a simple example for the Hasse diagram. First example, we'll take some simple example. Okay, so reduce the numbers of set A equals to 1, 2, 3, 4, 5, and 6, and consider that relation R is equals to X divides Y. The same relation we have taken, but we have reduced the numbers so that we can understand the Hasse diagram more clearly. Okay, so first we will try to draw the diagram of this. Okay, so first draw the diagram. 1, 2, 3, 4, 5, and 6 here. So these are the elements of the set. So one will have the age to 2, one will have the age to 4, one will have age to 3, to 5, and to 6. So one will have age to all the vertices, isn't it? Because one divides each number, and one will have this self age also. So this is your first number that we have selected, 1. Then next select 2. 2 will have age on 4. Then 2 will have the age on 6. Am I right? And 2 will have a self age also because 2 divides 2. Okay, so this is about 2, 4, 6, and self. Then next element select as 3. So 3 will divide itself, and 3 will divide this 6. Is there any other age possible with 3? 3 will divide 3, and 3 will divide 6. That means only 2 edges. Then next element you will consider as 4, but 4 doesn't divides any number out of this except 4 only. Similarly, 5 will divide 5 himself, and 6 will divide 6 himself. Okay, so this your diagram. So this actually is we are not going to prove, or if you want to prove, let us prove this whether it is poset or not. Poset means partial order relation. Poset means it is a partial order relation. Okay, so first let us check the properties. Reflexive. So is the relation reflexive? Every vertex have the self edge. Every vertex have the self edge, so it is a reflexive. It is an antisymmetric. So for antisymmetric, you have to check whether there are backward edges or not. So if there is a backward edge, then any of the backward edge. If there is a single backward edge also, if 1 to 2 is there and 2 to 1 is there, then we will not say that it is antisymmetric. But here you can see that 1 to 2 is there, but no backward edge. 1 to 3 is there, but no backward edge. 1 to 4, 1 to 5, 1 to 6, but no backward edges. Similarly, 2 to 4, no backward edge. 3 to 6, no backward edge. That means it is a antisymmetric also. Am I right? And last is a transitive. So transitive means 1 to 2 is there, 2 to 4 is there. So there is age 1 to 4, 1 to 2, 2 to 4, and 1 to 4. So it is forming a cycle like this. Then 1 to 3, 3 to 6. Then there is age 1 to 6, 1 to 3, 3 to 6, and age 1 to 6. Is there anything else? Okay, so 1 to 2, 2 to 6, there is age from 1 to 6. That means this is a transitive relation. Transitive means A comma B, B comma C, then A comma C must be there. Okay, so this is a transitive. So that's why this relation is a reflexive relation, self edges, antisymmetric, no backward edges, and a transitive. There are loops here 1, 2, 4, and 1 to 4. 1, 3, 6, and 1 to 6. Then another 1, 2, 4 that I have told you, 1, 3, 6. And 1 to 6 and 1 to 6. That means this is clearly a transitive relation also. Okay, now next we have to study the Hasse diagram. So let me create one more page. So this was our original diagram, and we are about to study the Hasse diagram. Okay, so let me check how many of you are in the class, because we are taking the new topic. Okay, so next topic is a Hasse diagram. So in Hasse diagram is used. Hasse diagram. The purpose of Hasse diagram you will understand. Purpose of Hasse diagram is minimize graph of poset. Minimize the graph of poset. Poset means partial order relation. Partial order relation is also called as the poset. So to minimize the graph of poset, this Hasse diagram is used. This Hasse diagram is used to minimize the graph of poset. Okay, now how to draw this Hasse diagram? Okay, so if you observe here that we are saying that we are using this method for minimizing the graph of poset, and the properties of poset or the partial order relation are, what are the properties? Poset should satisfy the following property, which reflexive, then antisymmetric, and then transitive. Reflexive, antisymmetric, and a transitive. Okay, so meaning of poset is satisfying all these properties. Poset is satisfying all these properties, and Hasse diagram used to minimize poset. Okay, so let us understand how this diagram is minimized. So let me paste it one more time. Okay, so in your original graph, these were the edges, original diagram, these were the edges. Okay, now we know that this diagram is of poset. This diagram is of poset, that means of a partial order relation, and it is satisfying this property. It is satisfying these properties. Okay, means if it is satisfying these properties, then there is no need of explicitly telling that it is a reflexive. Which edges are telling that it is a reflexive? So the self edges are telling that it is a reflexive. So you can simply remove this self edges. Remove this self edge. Okay, meaning why we have removed, because we are minimizing this graph. We are minimizing this graph. So minimizing this graph means we are decreasing the number of edges in the graph. So we know it is a poset. We know it is a poset. So there is no need of drawing the self edges, because already it is a reflexive. So it is not required to draw the self edges and show that it is a reflexive relation. We know it is a reflexive. So that's why we are removing the self edges from the nodes. Okay, so this reflexive edges we have removed. Okay, so the first task we have done. Now next task we have to do is, it is a transitive. So we have to remove the transitive edges also. So we know that the relation is transitive. We know that relation is transitive. That means if there is an edge from 1 to 2 and 2 to 4, then there is no requirement of drawing the edge from 1 to 4, because this is a transitive edge. Let me write this edge is a transitive edge. Similarly, from 1 to 3 is there, 3 to 6 here, then this also is a transitive edge. This also is a transitive edge, 1 to 6. Then which one is a transitive? 1 to 3, 3 to 6. Similarly, 1 to 2, 2 to 6, and then 1 to 6, the same edge is a transitive edge. So if you remove this transitive edge also, then graph can be minimized, because we know that this edge, as it is a transitive, poset is a transitive. So that means these edges are not required. These edges are not required. Okay, so we have minimized this graph. Now one more thing is required here. So this transitive edges we have removed. One more thing is required, that in this graph is a diagram. This graph is a diagram. That means it is showing the age is from 1 to 2. This age is from 1 to 2. We will not say that this age is from 2 to 1 because it has clearly showing a arrow here. It is clearly showing a arrow here. So that's why we'll say that this age is from 1 to 2. This age is from 1 to 5. This age is from 1 to 3. And this age is from 3 to 6. Now this directions also can be removed from the graph. So let us try to draw a new graph here. Okay, so whatever is the list element which have the relation on, because we have relation on 1 to 2, 1 to 3, 1 to 4, 1 to 5, 1 to 6, 1 to 4, and 1 to 6 we have removed because those are where the transitive edges. So let us draw this. This element we will write it as 1. This will write it as a 1. Okay, so the this graph Hasse diagram is read from bottom to the top. It is read from bottom to the top. So first edge that we will show here is from 1 to the 2 without a arrow. So this edge is without arrow. So meaning of this edge is, so if 1 is to the bottom, meaning is the relation is from 1 to the 2. The relation is from 1 to the 2. So that's why it doesn't require a direction. Whatever is the bottom node, that we will call it have a relation on the top node. So this direction, even though we are not showing the direction, this relation is from 1 to the 2. Okay. Now next element that we will write is as the relation from 1 to the 3. Then one more element is there that we can write here or add here, that 1 to the 5. Okay. So we are not showing the direction, but still it is saying that relation is from 1 to 2, 1 to 3, 1 to 5. Okay, now next. So this 2 have the relation over 4. Then this 2 have relation over 6, as well as 3 have relation over 6. So first we can draw this 6, which is common between 2 and 3. 6 is common between 2 and 3. So that's why we are drawn 6 here and joining the edges, because we have a relation from 2 to the 6 here, 2 to the 6 here, and 3 to the 6 here. So we will have a common edge there. So this is the upper level. So at the first level, we have only one node. Then at second level, we have 2, 3, and 5. We have 2, 3, and 5. And one more relation is we have not written. That is 2 to the 4 here, 2 to the 4. So this relation we can draw as 2 to the 4 like this. So this is the first level nodes, level 1. These are the second level nodes, level 2. Level 2 are 2, 3, and 5. And this 4 and 6 are on level 3. Level 3. This you are not required to write, but for your understanding, I am showing that these are the different levels. So this is your Hasse diagram. So I hope that you have got the procedure of drawing the Hasse diagram. So let me explain a little more about this Hasse diagram. These are actually not part of the diagram, so that's why I am removing it. So this is your final diagram. This is your final diagram. Okay, so let us understand. So first you will be given a diagram, or you will be given a relation on which you have to draw the diagram. And then what you have to do? You have to remove these reflexive relations, reflexive edges. So which are the reflexive edges? The self loops are the reflexive edges. So we have removed the self loops from each of the node. Then next task you have to do is remove the transitive edges. So we had the edge from 1 to 2, 2 to 4. So we have removed this 1 to 4. In previous graph, there was edge from 1 to 4. So we have removed this 1 to 4. Then we have another transitive relation as from 1 to 2, 2 to 6. So we have removed this transitive edge from 1 to 6. Okay. Similarly, 1 to 3, 3 to 6, the transitive edge was the same, 1 to 6. So we have also removed that edge. And then you have to remove this arrows also. So how arrows are removed? So by writing the different levels of the node. So one have relation over all the limits. One have relation over all the limits. So we are writing one at the bottom. Then this one have relation to 2, one have relation to 3, and one have relation to 5. 1, 2, 3, 5. So meaning of this is one is related to 2, one is related to 3, and one is related to 4, 5. That means His diagram is read from bottom to the top. So that's why the directions are also not required in the His diagram. Then this 2 have relation to 6, 3 have relation to 6. So this we have represented as common relation of 6. So 2 have relation 6 and 3 have relation 6. And finally, 2 have the relation over 4. So this is your complete Hess diagram. So let me know in the chat box whether you have got this Hess diagram or not, because this Hess diagram is required to understand the next topics that we are going to study as lattice and chain and anti-chains. So for that reason, you need to have a clear idea of the Hess diagram. Okay, let us take some more examples for a Hess diagram. Okay, simple example we will take. The nodes are, let me write example. Set A equals to 1, 2, 3, 4, 5. And relation R is equals to X less than equals to Y. Relation is X less than equals to Y. So you can simply draw a diagram of this. So let me draw a diagram. 1 here, 2 here, 3 here, 4, and 5. So 1 is less than 2, so this edge, 1 is less than 4, this edge, 1 is less than 5, this edge, and 1 is less than 3. Next, 2 is less than 3, 2 is less than 4, and 2 is less than 5 here. Then next is 3 is less than 4, and 3 is less than 5. 4 is less than 5. And every element is less than equals to himself. So 1 is less than equals to 1, 2 is less than equals to 2, 3 is less than equals to 3, and 4 is less than equals to 4, and 5 is less than equals to 5. Okay, so this is a diagram of this, and with this diagram you can say that this is a poset or the partial order relation. No need to check here because it is a reflexive, self edges are showing, it is anti-symmetric because no backward edges, and it is asymmetric because there are the cycles like this 1 2 4 and 1 to 4, then 2 4, sorry 2 3 4 and 2 to 4, 2 to 3, 3 to 4, and 2 to 4. Okay, so this you can convert in the Hess diagram easily by removing everything, and then you can write the edges. Okay, let me directly draw this Hess diagram of this, so it will be a simpler. The bottom node is 1. This is level 1 node. So 1 is less than 2. 2 is less than 3. 3 is less than 4. And 4 is less than 5. So this is a simple Hess diagram for your relation, given relation. So there are 5 levels, 5 different levels. So no need to draw this 1 to 5 edge, 1 to 2 edge, 1 to 3 edge, 1 to 4 edge. Similarly, 2 to 3, 2 to 4, 2 to 5, 3 to 4, 3 to 5, 4 to 5, and 4 to 5 edges, and the self edges. So you can draw this Hess diagram with simplicity. Okay, so you can also directly draw this Hess diagram without drawing the diagram or then removing the reflexive edges, removing the transitive edges, and so on. So let us understand one more example of this, in which we will directly draw the Hess diagram. So question is draw the Hess diagram So if you have any doubts, you can post in the chat box meanwhile. So we can take those doubts if you are not understanding this Hess diagram. It is very simple to draw the Hess diagram. So if you are not understanding, then you can post in the chat box meanwhile. I am writing this question. Here, S is our set of 1, 2, 3. And relation is A is proper subset. A is proper subset of B. A is a subset of B. A is a subset of B. So this is the relation given. R is equals to A subset of B. Okay, so in this, let me check. In this diagram, in this example, they have asked us to draw the Hess diagram for S less than equals to. So your coset is represented by this symbol, S comma less than equals to. So this means it is a coset. This means that this relation is a coset, partial order relation. Partial order relation. So here S is a power set of 1, 2, 3. S is a power set of 1, 2, 3. And the relation is given is A less than equals to B. So first we will try to write a set S. So S is a power set of 1, 2, 3. What is meant by power set? So it is having the 3 elements. The power set will have how many elements? 2 to the power 3. That means 8 elements. It will have the 8 elements. So which are those 8 elements? Can you tell me? So first element will be a 5. Second element will be a 1, set of only 1 element. Third element will be only a set of 2. Then set of element 3. Then next 1, 2. Then next 1, 3. 1, 3. Which one is remaining? 2, 3. And finally, one more element, 1, 2, 3. Am I right about the power set? So these are the elements of set. How many elements? 1, 2, 3, 4, 5, 6, 7, 8. Okay, so we have considered all the elements of the set. And what your relation is saying that A is subset of B. A is subset of B. Okay, so which is the element that we should draw at the bottom? Which element we should draw at the bottom? The element which is subset of all. So phi is subset of this set, phi is subset of this set, phi is subset of this. So at the bottom we have a element as a phi. Okay, so this is the bottom element, or we will draw this as a node, and we'll say this as a phi. Okay. Then which are the next level nodes? Which are the next level nodes? 1, 2, 3. These are the smaller sets. So this one is subset of this, one is subset of this, one is subset of this, 2 is subset of this, and 2 is subset of this. So okay, so let us write this. So this phi is subset of 1. Phi is subset of 1. Am I right? Then this phi is subset of 2. And this phi is subset of 3 here. So these are the second level nodes. 1, 2, 3. Okay, now let us try to write the common element between this 1 and 2. So this 1 have 1 is the subset of this set. Am I right? 1 is subset of this set. So this we will write as 1, 2. Similarly, this 2 is also a subset of this. So we will draw this page as 2 is also a subset of this. Okay. So similarly here we will write 1, 3. So sorry, instead of 1, 3, we will write here as 2 comma 3 because 2 and 3 should be a common so that we can draw a neat edge. So this 2 to the 3 and this 3 to 2 comma 3. So this up to this we have done. Now one more element is remaining, that is 1 comma 3. One more element is remaining, that is 1 comma 3. So 1 comma 3 we will draw at the center. 1 comma 3. Let us write this at the same level of this nodes. 1 comma 3. And which is the edge? It is from 1 to the 3 and it is from this 1 to 3. And finally, we have only one node remaining, that is this 1 to 3. So 1 to 3 will be the top node. So let us write this 1 to 3 here. 1, 2, and 3. So this 1 comma 2 is a subset of this. 1 comma 3 is a subset of this. And this 2 comma 3 is also a subset of this. Okay, so this is how we will represent a Hasse diagram for this. Hasse diagram for this particular relation. Hasse diagram for this particular relation. So is it clear now how to draw the Hasse diagram? We are not required to draw this edge 1, 2, 1, 2, 3. This is not required. Why it is not required? Because this is related. 1 is related to 1 comma 2 and it is related to 1 comma 2 comma 3. And this is becoming a transitive edge. This is becoming a transitive edge. So we don't require the transitive edges. We don't require the transitive edges. Similarly, this 3 is doesn't requiring this edge. This 5 is doesn't requiring direct edge to this. So whatever the transitive edges are there, we have to just remove those edges. We have to just remove those edges, and we have removed those transitive edges and drawn the Hasse diagram for this. Okay, now let me give you one example of this, and for which you have to draw the Hasse diagram, and upload that Hasse diagram in the attendance link. Okay, so let me give you one example and check whether you can be able to draw or not. Example is, so you are not required to prove this example. A equals to 1, 2, 3, 6, 9. 1, 2, 3, 6, 9, and relation is equals to x divides y. Simple example, x divides y. So prove that it is opposite. Prove it is opposite and draw Hasse diagram. Prove that it is opposite and draw the Hasse diagram. Set A is given 1, 2, 3, 6, 9, and R is given as x divides y. R is given as x divides y. So you should be always using the direct method if you have understood how to draw the Hasse diagram. Hasse diagram doesn't have reflexive edges. Hasse diagram doesn't have transitive edges, and Hasse diagram doesn't have the arrow graphs. That is diagrams. There are no directions on the edges. So these three things you should remember, that in Hasse diagram there should not be a reflexive edge, there should not be transitive edge, and there should not be a direction. Then only it will be called as the Hasse diagram. So solve it for this example. Meanwhile, I will create a quiz